In today's episode,
I will coin the term hyperplexing.
a look behind the scenes
Yeah, we had archives in archives in archives and so on.
on how complex tools
I don't know all of them.
It's a lot.
are built to spec
We had many issues with.
for deep troubleshooting.
No, like you said, we suck at it.
I joined this project and I think I never left.
Welcome to Cisco Tech Stories. A podcast with real-life stories from real-life engineers. Your hosts are Nicholas and Tristan.
Hello and welcome to episode 20 of the Cisco Tech Stories podcast. We're your host, Nico and Tristan, engineer at Cisco EMEA. Hello, Nico.
Hello.
All right, so today we are welcoming yet another fascinating Cisco engineer. And that's one of the things that I like with Cisco is the diversity of the profiles and backgrounds of the people that we got. In the past, most of the previous interviews that we had were from network engineers. But today we're not interviewing one. Today we are interviewing Jonathan Slenders. Jonathan is our Python software development expert in Cisco CX. He's the one who brought structure, rigor, and professionalism to all the scripting that we do at Cisco Tech. He is a key player in the transition that we did in Cisco Tech to automation by training, teaching, and helping tech engineers with all their Python programming challenges. And on top of that, Jonathan has been a lead developer on many Cisco tools, such as Redkit and Candela. We will talk about those in a few minutes with Jonathan. So stay tuned because this will be yet another great episode.
Hello, Jonathan. How are you doing?
Yeah, doing good, thank you.
Hello, Jonathan.
Can you tell us how you came to work for Cisco? Because you're one of the rare people who's not a network engineer at Cisco. So how did that start?
Yeah, that's right. It's I think about 10 years ago now. I started as a Python coach, Python teacher. So I had back then already a background of Python programming for about 5 years, I think, professionally. And so I was hired actually to help network engineers write Python code. So all these engineers, they were very skilled in network infrastructure, networking stuff. But they did not have any actual professional coding experience. And so I was hired to help them out write proper Python code for whatever they had to do. And so back then I was coaching lots of engineers in Brussels as well as in Krakow. And after a while I started giving Python training courses. So that was very interesting.
I remember that's how you were sold to us. Like we have a Python guru. Like any Python problem you have, check with Jonathan. That's how we were told about it. Is it correct to say that a lot of engineers actually managed to do some Python themselves? Like they self-learned it, but quality then was the problem. Like they are not experienced with the right way to program, with scalability issues or a bunch of stuff we had no idea about.
Yeah, that's right. I've seen many, let's say, creative solutions of writing Python code.
Bad code, you say?
Bad code, code that worked, but not maintainable, not clean. Like I've seen very interesting things, like for instance, spawning a subprocess of /bin/echo for printing stuff. So every print would do a subprocess call, which worked, but it's not the right way of writing Python code. But yeah, it was very nice to work with these people. They were very intelligent. They were able to learn, and so yeah, I got to help them.
And maybe you can tell what was the main reason why engineers have to write Python scripts during their day job.
Yeah, back then Cisco was at a transition period where it moved more from a hardware company into a software company. And so rather than having engineers deal with hardware issues, we wanted them to be able to automate stuff and write code for whatever problems they were facing. And so in order to support that transition towards more of a software company, they had to be reskilled, re-educated.
Mhm. And also, like you said, this was to automate part of the job. So like whenever an issue that comes once, we write a script for it to detect it. And then next time the issue happens again, that automation was supposed to detect it automatically so that it speeds up the resolution process and things like that, right?
That's right.
And I think that brings us to your first big project. I don't know how long you worked as just a coach, if I can say so, before moving to a project. But back then, everything was done manually with log files. I remember, like, you have a case, you ask for logs, you solve the case with the logs, and then we have a knowledge base, and that's about it. Then we started with some automation scripting and then augmentation tools as well, because going through a huge log file is also not very easy if you do it just manually. So we started to home code some of these tools, but like you said, not always scalable, not always the right way. But even if you automate some stuff, that's for the known issues. You also always need to manually go through the logs at some point. Even if augmentation helped you pinpoint you to an area of the problem, you need to manually open the logs. And cannot remember the year exactly, but we had issues with our laptop, opening very large text file, and people like, oh, I'm looking forward to have my laptop refreshed to have the 16 gig of RAM to be able to open a 4 gig text file. And then people were just doing grep in the command line to find stuff in it, like really primitive, if I can say so. Now that I look at it with 2025 eyes, really primitive ways. So that, I think that's where you had a big project, right?
Yeah, there were a couple of tools that went hand in hand. So on one hand, we had a scripting platform where people could write Python code within the web browser, and that would run somewhere on a server. And this code would be able to access files in a file storage that we had there. But we also needed to have a way to view these files remotely. And that was not feasible because these files were literally gigabytes, sometimes even terabytes in size. And there was no way you wanted to download any of these files. And if they were archives, extract them and search through these files. So we wanted them to stay on a network server remotely. And also because we had some engineers that were working from home remotely over slower internet connections, for them it was totally not feasible to download gigabytes in size, even if they had the disk space. So we wanted to have a tool that engineers could use to view the content of big archives and files remotely through a web application. And so that was the Candela project I was involved back then. And it allowed the engineers to traverse the remote file system, look into these archives, open these archives, and see the content of these files, just streaming the fragments that they wanted to see to the web browser. So even if the files were gigabytes in size, they would just like stream the fractions of the file into the web browser with as little latency as possible. Because if you are scrolling through the file, you don't want that, like every time you scroll, that it takes seconds to fetch like the next fragment. You want to have a feeling that it feels like viewing a local file, right?
I already have
And
so
when-
many
when you
questions
say-
because I mean, the very naive view would be like, instead of my laptop opening the file, it's just a powerful server opening the file, but it would still like open the whole file in its memory. And maybe that's already too naive, and it already loads it in a much more efficient way than that. I don't know. But also there's the streaming part you said, because if I want to scroll through it has to send that data live to my screen as quickly as I'm scrolling. So that's really problematic, right?
Yes. So there we had a WebSocket connection from the web browser to the server, over which we could stream in real time fragments of the file while the user was scrolling through the file. And while the user was doing that on the remote end, on the server, we would fetch these fragments from the file and send them back to the WebSocket. But in order to do that, we needed to have some kind of line index. We needed to know where in the actual file which bytes actually corresponded to which line numbers. So if, let's say, the user was requesting line 1000 to 2000, we had to translate these indexes to byte offsets in the remote file, so that we did not had like to process the whole file over and over again. So on the server, we would keep a track of such a data structure, a mapping from line numbers to byte offsets. Now, something very interesting there is that all of this is actually a streaming architecture. So the file server, or the Candela server actually, would do a lot of processing while the user is loading the file for the first time. So the first thing it does is downloading the file from the actual file storage. And then if it is an archive, it would extract the file. And then if the user was addressing one of the files within the archive, it would extract that file from the archive. So before building a table of content, then extracting the file. And then it would even do some UTF-8 normalization, because we had so many different encodings, like UTF-8, UTF-16, other things. In order to present all of that, we needed to have like a standardized format that the rest of our code base would support. So we had to do a translation to UTF-8 if the encoding was not UTF-8. And then we had to build a line index, keep that data structure in memory, and store the file in disk in the remote application. And all of that happened at the same time while the user was loading the file. And so a consequence of this is that we had very low latency when the user was navigating to one file. I mean, while the file was still downloading remotely from the file storage into the Candela application, the user could already view like a portion of the file, the portion that was processed. So in a couple of seconds, we could already present something. And at the same time that the whole line index was still building on the server, the web browser would be informed that more lines would become available, and the users could scroll downwards in the web browser while the file was still being processed on the server. And so that's a lot of concurrency, a lot of things taking place at the same time. But this allowed us to have a very responsive application that could present something as quickly as possible to the end user.
Who knew that displaying a text file could have so much complexity behind it, right?
Especially with such a huge file size.
Yeah, indeed. And what are the technical solutions that you use in order to do this streaming? So you mentioned WebSocket. What else do you guys use?
Yeah, so the application itself is written in Python using async.io. And we use async.io because that allows us to do many things concurrently. With concurrently, I mean doing things at the same time. Like we have all these concurrent data flows, the extraction of the file, the building of the line index, UTF-8 normalization, maybe building a table of content from the file, things like that. All of that had to happen at the same time. And so in the application, we were streaming from one component to the next component. So we had many producer-consumer approaches within the application. And so that's something that async.io really excels at. So if you want to do these kinds of concurrency, then something like async.io is really great.
And what would be the because whatever you say here with async.io, it sounds very much like threads. So what would be the difference between async.io and plain threads as we know them?
Yeah, threads, that would be another possibility. You can use threads for having concurrency as well. But there are a couple of trade-offs. Like threads, they always come with some overhead because every thread has its own call stack. And so maybe you can have 1,000 threads, but you cannot have 1,000,000 threads. The overhead is too much. With async.io, that's not a problem. You can have 1,000,000 concurrent coroutines running at the same time. So if you have this amount of concurrency, then async.io usually works better. But there are also a few other reasons, like threads, for instance, they cannot be canceled. If at some point you say, we no longer want to proceed with this operation because the user closed the web browser. Or we don't no longer need to see this file, or at some point we want to discard something and we want to release the resources. We cannot kill a thread because killing a thread means that if the thread had acquired some resources, probably the cleanup of those resources would not take place. So we would leak things over time. And so async.io has a built-in way of canceling things, which is called cancellation. So it's pretty easy to cancel things. And another nice advantage of using async.io is that it has what we call checkpoints. And checkpoints are places where we do a context switch from one flow to another flow. So if we have many concurrent flows and we want to go back and forth between those two, with threads, we don't have any control over at which point we do a context switch from one thread to another thread. So that's basically the operating system saying like, now we're going to move to the other thread. And with async.io, you have like these explicit checkpoints. In the code, you see them as the await keyword. And typically that's where we do I/O. So if we at some point have to wait for I/O, like wait for a network packet to arrive in one flow, that's a good time to switch to another task, another concurrent task. And so by having these explicit context switches, we know that within 2 checkpoints, everything runs atomically. And so if we are manipulating data structures, we know that nobody is going to interfere between 2 checkpoints. And so we can do the manipulation of data structure. We know that no other thread or task actually is going to interfere, and we will ensure that we end up in a consistent state. So if, on the other hand, you would use threads and you have many threads all trying to access the same data structure, then you have to put locks in place. You have to ensure that these threads will not modify the same data structure at the same time, so you wrap them in a lock, and that way you have the same kind of consistency. But with async.io, you know your checkpoints, so you know your context switches, and in many situations, you don't need to have locks.
I have a funny question. Since Python is made with a lot of C, are async.io made with threads in the background, but then with a structure on it, to make it work differently? Or is it like a complete different system? I mean, at the operating system level, like...
At the operating system level, it's only one thread. So all these concurrent flows, they're actually interleaved and they run on top of one operating system thread. And that's exactly the reason that we know that whatever takes place within 2 checkpoints, nothing else will take place at the same time. Now, you might say like it means that we only leverage one CPU core.
Yes.
If you have a CPU with many cores, we're only taking advantage of one CPU core. And actually, it doesn't really matter in Python because that's a problem anyway. Even if you use threads, Python has the GIL, which means that Python instructions require the global interpreter lock. And because of that, even if you use threads in Python, only one thread gets to operate on Python data structures.
Okay.
And so these threads would anyway compete for the same lock. And so the consequence would be that you would only be using one CPU anyway in
So
Python.
it makes Python threads completely pointless then in comparison.
To some extent, like if you have C extensions in Python, those C extensions could do operations that don't require the GIL. And in that case, you could leverage an additional CPU. And also with async.io, actually. With async.io, if at some point you have to do something which is really CPU bound, you don't want to block the event loop. And so in that case, what you could do is run the CPU bound code on a separate thread, which if it uses a C extension would maybe not require the global interpreter lock. And that way you would not block the event loop. And at the same time, you could leverage additional CPUs.
I find it to be a very interesting topic. I mean, even for a network engineer, because we always think, oh yeah, this new appliance has a gazillion CPU, we're good. But depending on the workload, sometimes that workload is only using one process, and then you can have as many CPUs as you want. It's no magic is going to happen. Then you only get benefit if you have different workloads that each are going to use one CPU. And so the concept of high CPU, we always think 0 to 100%, but you have to think high CPU core or a process on high CPU usage. So network engineers have to evolve to understand that and use the proper wording, because it really matters.
That's right, yeah. And a lot of research is being done these days into making Python take more advantage of all the additional CPU cores, but it's an extremely difficult topic.
It adds complexity, obviously, yeah.
Yes.
And risks. Okay. I have another stupid question about Candela. It seems like, was Cisco the only one with the need to do something like this? Like, there was no application in the market that streams large files like this? Why coding one from scratch?
I honestly don't know. I've been looking around, but I didn't find anything that did exactly this. So I'm not sure. Maybe there are. In the end, the advantage of doing it ourselves was also that we could integrate with other Cisco-specific tools.
Absolutely where I was going. I'm sure that by now that solution exists, right? Back then, I don't know. But by now, there's plenty of solutions, but they will be typically proprietary servers and a complete massive solution. So it's going to be harder to integrate. And I don't think something we talked about, but the origin of the Candela application was really, like you said, the streaming and the efficiency for large files. But then it added also a layer of collaboration, because now when we open a log file, we can comment some lines and then highlight it for other engineers if we work on a case. Because it's more and more common as complexity increases. We need more engineers to work on the same case, different specialties, and then it allows us to collaborate a lot better, which regular text editor don't do anymore.
That's right. Yeah, we had these kind of integrations.
And so you mentioned all the backend architecture using Async.io and Python code, but what about the front end? How do you stream that to a web browser, actually? So the only thing we have is JavaScript, right?
Yeah. So the front end is a typical web application which uses, in our case, Vue.js, something similar to React. But the things which are special there are that on one hand, we use WebSockets for the communication to the backend instead of REST API calls, because we want to stream data. For instance, if let's say we open an archive on the remote side and Candela is building a table of content, it will do that while the file is still being downloaded. And it will take some time to build a table of content. And so we're actually pushing all the entries from the table of content one at a time to the web browser once we encounter them in the server. So the request to build a table of content, it's not just request response. We do a request to build a table of content, and the response consists of many small chunks of data, each time containing one table of content entry. So we use the WebSocket for the communication there. And something else which is probably unusual is the way that we do the rendering. So in order to efficiently render such a text file, we could not use the standardized DOM operations. Like, on a web page, all the visual elements are composed of DOM nodes. So you have a paragraph, you have a div element, and so on. You have all these HTML elements. And so if you scroll through these files, if you would represent your file using DOM elements, it would mean that we would have to constantly update the HTML DOM, replacing paragraphs, maybe replacing like characters at a time. And that's something very expensive. We could not have like an HTML element for every single character or something like that. And so we did our own rendering engine using an HTML canvas, painting literal characters on the screen within the canvas. And so when the user would scroll through the file, we would compute a diff of what the screen looked like before and after, and we would update only those positions at the screen where a new character had to be displayed.
So you're telling that basically the way that the text is displayed on the screen is not by writing text, but by building a picture? So like you're streaming a picture eventually, or?
We are rendering a picture in the web browser based on the
Oh.
view that the user has at that point in time. And when the user scrolls through the file, we update that picture.
So the canvas element, that's the one used for SVG graphics, right? That's the one you were talking about.
Canvas is not used for SVG. I believe for SVG you have a specific dedicated SVG element.
Okay.
But the canvas is like a two-dimensional picture in which you can draw pixels or paint characters or whatever you want to paint. And so for every character that we had to paint, I think we built it some kind of cache so that we could say, paint this character at this location.
This is amazing.
Now, interesting there is also how to make selection work, because you want this to feel native. You don't want this to feel like a picture that the user is looking at. So you want end users to be able to select text using the mouse. You want them to maybe be able to double click to select a word or triple click to select a paragraph. And so we had to implement these kind of things. We had to respond to mouse events in order to make the selection work. And when the user was selecting something, we had to display it as selected text with like a blue background, something like that. Even the selection could like span a region much wider than it was currently visible on the screen. Like if you have millions of lines, you don't have those millions of lines on the screen, but maybe the user would select first a part at the start of the document, then scroll to the end, then do shift click to tell that the selection should end at that point. And so everything in between would be considered selected, even though the web browser didn't even had all these lines in memory, right?
It sounds crazy to me to use pictures to render text, but on the other hand, if you were to use text, it wouldn't be easier because you don't have all the text at any point in time. So you need to stream a lot of text and then delete some part and add it. It would be a mess as well to just use text. So I guess picture makes some sense.
Yeah, we did some experimenting before using the HTML DOM and some continuous scrolling, but it was really hard to get some decent performance. And then when we transitioned to using the HTML canvas, the difference was really noticeable. And we are not the only one doing that because, for instance, Visual Studio Code, they also use the HTML canvas, I believe, to render the terminal in Visual Studio Code. It's the same idea.
What amazes me is that despite all of those things that appears to be overhead compared to simple text rendering, you're still more performant than using HTML DOM engine for that. This is simply amazing.
Since this podcast is about troubleshooting stories, I've heard that caching was not a trivial. It was a requirement, not a trivial feature with Candela, and it led to some issues. Like I've heard problems about that. Did you have, like a naive mind? Oh yeah, let's do caching. It's going to be great, and then face much more problems than you anticipated, or?
Oh, we did. So the problem with caching is always that you have to do cache invalidation. At some point, you have to release information from the cache. Otherwise, the cache will keep growing over time, and you'll run out of memory.
It's not a cache; it's your entire hard disk. Then
we had to cache any file that we were downloading in memory because users, for instance, they would open multiple tab pages each time with the same file, or we could have situations where multiple users would even access the same file. And we didn't want to process the same file over and over again, especially not at the same time. So if we had multiple users trying to access the same file at the same time, we would only download once, only extract once, only build the line index once. And then we would serve from the data structures that we have in memory at that point. But it's required, putting logs in place, like in many places, to prevent doing the same processing multiple times at once. And so also on disk, we built that cache of the files that we had downloaded in the Candela web server, like the files that we extracted from the archives, for instance. But yeah, at some point we have to clean up things that we think are no longer needed. And so a way to do that is very simple, to keep track of like an access time for every file. And at some point, if you run out of space, you look at which are the oldest files and you remove those. But it's not so simple because it's an ongoing process. It's operating on these data structures. Some things are being modified while you're accessing these data structures. There are all these concurrent flows.
Mhm.
And so we had many issues with ensuring that we were not leaking anything. And something which is also very complex there is that there is kind of a parent-child relationship between these files. Like you have an archive and then you have a file within the archive. If you clean up, you cannot clean up the archive before cleaning up the file within the archive. So if you look at the data structures as a tree, but similar to a file system, if you would do some kind of cache invalidation, you would always have to focus on the leaf node first. Look for the oldest leaf node and then discard that one. Then again, look for the next oldest leaf node and discard that. And this process was also pretty CPU intense. I don't remember the reasons why, but it's something that we had to do regularly. And we had issues that with phrasing the event loop. So a problem with concurrent applications that use an event loop is always that if at some point you do something that is consuming CPU for an extended period of time, then you freeze the event loop and it will block all the concurrent tasks, right? It's only when you're done processing that you can do a context switch to any of the other tasks. So doing CPU-bound stuff in the event loop is problematic, but cache invalidation, that was one of them. And there was no way to do that outside of the event loop on the helper thread because it was interacting too much with the data structure that we had there in memory. So that was a difficult problem. We had to do a couple of iterations to optimize this process and to make it efficient.
I remember now a specific device where the log bundle, which is a log archive, would contain text files, but also archives inside it, which would contain also log files and sometimes another archive inside it. That's the kind of nightmare that you need to keep track of all of that. What is opened?
We had archives in archives in archives and so on. And then the text files in there often also had some kind of compression, like gzip compression or something like that. So they were compressed as well.
How do you search in such a massive file? Because it feels to me like you need to anyway open the whole file and do it sequentially, but
yes, more or less. So searching is something that we had to do on the back end, right? So it was initiated
because your browser only has a few lines only at a time, right? So.
Yes. The search operation, of course, was started from within the web browser. It is also always a user doing a search, but we had to perform the actual search on the back end. And then as a result of the search, we could return line numbers so that the web browser could jump to that specific line number and then display that portion of the file. But actual search is taking place on the back end. And basically, if I recall correctly, we were memory mapping the file and then running regular expression over the memory mapped file so that we did not have to take everything in memory for searching. And that worked pretty well, but also there, searching is a CPU-bound operation. So we had to use the regex library, not the RE library, because the regex library releases the global interpreter lock. And so because of that, we could run it on a separate thread. So that even if the searching would take like a longer time, that it would not block the event loop.
I was amazed. You say a long time, but I was amazed. All my Candela searches are only seconds. Like it feels barely even slower than my search on my laptop. But I don't open 5 gig files on my laptop. So
yeah, that's mainly thanks to that library, thanks to the regex library. It has a very performant regular expression engine built in.
I have I mean, this episode is already taking some time, so I want to move to the other project that, at least that I know, big project you're working on, which is RadKit. We already made an episode in this podcast about RadKit. How did you come to work on RadKit? Because as far as I know, it was a one-man idea that another guy started to promote and say, "Oh, we can make something out of it." So you didn't come first in the project, did you?
No, I did not. I was working on a couple of other projects in between, like a few smaller projects. But I was in touch with the people developing RedKit. And then at some point, I think they asked whether I wanted to join. And I joined this project. And then I think I never left.
So how was it to inherit from an architecture decided by other people? Or you were actually having a voice in the early architecture already and it was okay? Or
No, I did not have a lot of influence over the original architecture. I was mainly watching from the sidelines. But then when I joined, I've been gradually over time redesigning some of the architecture because certain things had to be made more efficient. And so, yeah, I've been reshaping this project over time, but that's something that you do slowly because there is a lot of legacy in there, like features that have been implemented. You have to ensure that all these features keep working. You have users using these features. And so we've been reshaping the architecture. And there also, we've been making the transition to async IO. I don't think RedKit originally was using async IO. I'm not totally sure anymore, but we've adopting more and more async IO patterns within the code base.
I just want to maybe I'm going to do a very 20-second simplification of what is RadKit for people, because I mean it's kind of long to explain, but it's like a way to remote access your devices without using VPN through a cloud server, right? So anyone can you can actually share access to your devices to a specific subset of people. Those people will never know the device credentials, and all goes through the cloud. So it's no screen sharing anymore, nothing like that. You're not giving a VPN access to your entire network. You can give remote access to specific individuals for a specific amount of time and keep track of what they're doing. I think I did a decent job of summarizing it. So that, I mean, if you just say it like that, it sounds like a glorified SSH server, which is probably very insulting to say. But what big technical challenge did you have? Like, first of all, there's encryption, right? But is there any other big technical challenge that people don't think about when they think about RedKit?
Yeah, I think the way that we establish the connection between a RedKit service instance and any RedKit client, it's pretty interesting. So as you said, that's something that we do through the cloud because the cloud functions as kind of a bridge for those two because both RedKit service and RedKit client only do an outgoing connection to the cloud. And that's important because that way we can traverse a net firewall. And so the cloud will bridge the RedKit client and the RedKit service. And the protocols that we've been using for that, part of them are homemade, but they allow to have like a streaming end-to-end connectivity between RedKit client and RedKit service, completely end-to-end encrypted and with low latency as well. So that through these bridged connections, we can even establish like an interactive SSH connection or like expose a terminal session and be able to respond to keystrokes in real time. Like if you press a keystroke and the keystroke has to travel to the remote application in order to be echoed back, because that's what most terminal applications do. You want that round trip time from RedKit client to the cloud, to RedKit service, to the actual device, and all the way back. You want that to be as quick as possible. And so...
and still with encryption, end-to-end encryption along the way.
And so is it correct to say that you're actually simulating an end-to-end SSH session through, in reality, both devices, your client and then the network device, contacting the cloud? So it's outgoing to the cloud, but then you on top of that you're simulating a unique SSH, right?
It's
Is that
not.
fair to
We are not using the SSH protocol for that. So we're not simulating an SSH connection, but we're simulating a terminal
Terminal, yes.
connection.
So it looks
And
like an SSH session, but it's not
yeah,
SSH. Yes,
yeah.
okay.
To the end user, it looks identical.
And the benefit is that it's not only about SSH, right? Because you can do netconf, all of that. So that's why you're not tied to SSH, because you can do many protocols, right?
Yeah, we can do whatever protocol, and even for the future, if we want to add support for other protocols, that should be possible through this connection. So the protocols that we use for the bridging of Redkit client and Redkit service, the only thing that they know of is that there is a way to multiplex streams, concurrent streams between both of them. So we could, in Redkit client, do an RPC call to a Redkit service through the cloud. And within that RPC call, there would be an upload stream and a download stream. And you can think of like one interactive session, that would be one RPC call. So if we would open a terminal connection to one specific device, that would be one RPC call where you have those bidirectional streams, input and output. But if you were opening multiple connections to different devices, then for each of them, you will have such a set of streams. And we multiplex all of them through a single WebSocket connection that we have to the cloud.
Right, because even if, there's a lot of scalability dimensions, if I can say so, because you can be a single user and I'm accessing my device, but then you're building a script that will actually virtually SSH to several network devices, compare configs, and then do actions, based on several devices and at the same time. But then you can also be multiple users using the same Redkit service and managing the same devices at the end of the day, right? Without knowing someone else is running scripts as well. And then from a Redkit cloud perspective, you also have many Redkit services connecting.
Yeah, that's right. Yeah. So there are actually two layers of multiplexing even, because a Redkit client can reach out to multiple services. And for each of them, we need to have a separate end-to-end encrypted connection. Every pair of Redkit client and Redkit service is one end-to-end encrypted connection. And within that end-to-end encrypted connection, we then multiplex all the RPC calls. So you see there are two layers of multiplexing, of having concurrent streams. And at every multiplexing layer, we also need to have some kind of flow control because you want to avoid that head of line blocking. Like if a consumer of one stream stops consuming the output of a stream, you don't want that to prevent data flowing through the other concurrent streams.
I will coin the term hyperplexing for double multiplexing. How do you do HTTP proxy? Because people thought, oh yeah, it uses SSH, which you said it doesn't, and then you're just doing port tunneling. But I know with Redkit, you can actually do HTTP proxy and access through the web certain network devices remotely through an outgoing connection. So which is awkward to think about, but it's very handy. How do you support all of that? How does that?
Yeah, so before we implemented this, we already had support for TCP tunneling. One reason for that was it would allow us to support like any protocol. And that way we could have end-to-end TCP tunneling, and a Redkit client could reach out to any port of any device within the remote network, if it was given access, of course. But then we started to support the HTTP protocol. And so in Redkit client, first what we could do was reach out to any URL of an HTTP API of the remote devices. And so that was a simple Python API. We could perform a request. We got back a response. And later on, we decided, well, we could use this mechanism to actually present a whole web interface and reconstruct the remote web UI that we have on that device within Redkit client. Now, the consequence of this is that if you take a look at all the network traffic that a web browser is doing to the remote device, that are a lot of parallel calls, like every asset, every image, every JavaScript file, every CSS file, all of those are separate requests and responses. And in the Redkit protocol, that means doing a separate RPC call for every request, for every piece from the web page that gets presented. So yeah, the way that Redkit client does that is by locally exposing an HTTP proxy that you can configure in your web browser. And then through that proxy, you can navigate to any of the remote devices. And Redkit client will then accept the incoming HTTP request. It will terminate the TLS connection, the HTTP connection. It will understand the protocol, and for every asset that we request there, it will do an RPC call to the remote Redkit service where we request the same URL again. So there we kind of reconstruct the same HTTP session.
It sounds simple just to display a web page, but like you said, with all those parallel connection and streaming that happened in modern web pages, it turns out that it required a much more complex solution than what people might think initially, right? And it looks like you've been an expert in dealing with streaming things over the years with experience from Candela, right?
Yes, to some extent it's similar technology, similar problems.
Yeah, always coming back to streaming.
Also, with this HTTP proxying, there also latency was super important. We have web applications that required more than 100, I think, HTTP requests during startup. So you open your web browser, you navigate to that device, it does maybe 100 requests. And so we have to perform all those requests at the same time through this Redkit connection and multiplex all these streams with as little latency as possible. So they're doing a lot of optimizations there.
It's pretty amazing.
Maybe to wrap up, I also know that you have a personal project that actually I asked you once about because I was working on something that could use it. You were quite famous for the prompt toolkit, right? And I saw on GitHub you have like close to 10,000 stars, which is it's not bad. It's not bad. It's kind of funny that somehow your whole career revolves around similar topics, right? Because you did this prompt toolkit first on your side, then Candela, which is streaming. Then you have Redkit, which is kind of it's a prompt as well, and then it's also using streaming. So I mean, you're staying in the same domain. Is that like on purpose? Is that a coincidence or?
I don't know. I think it's probably accidental. Of course, at some point you specialize in certain things. I did a lot of things around terminal applications. So Prompt Toolkit is a library for building command line applications for the terminal. And one of the tools that we have built on top of it, for instance, is PT-Python, which is an interactive Python shell that gives code completion, syntax highlighting, whatever you want to expect from a richer terminal application to have a nice Python REPL.
And why did you build Prompt Toolkit in the first place? What was the need at the time?
Well, the point was definitely not to build a Python REPL or something like that. I also didn't expect that at some point I would build this, but the thing is that back then, that was from before I joined Cisco, I think 3 years before that, there was not a single Python library that could be used as a readline replacement, a GNU readline replacement for accepting input from a user and providing some kind of syntax highlighting in the input that the user types. And so that was a small project that I was working on back then. I don't think it's even anymore on GitHub. It was a tool for deploying applications to web servers. But I did some initial prototype back then of something which I wanted to have, and that turned out that became Prom Toolkit.
And
So it's simple, just a case of you have a problem, you spend some time trying to fix the problem, then turns out that other people have the same problem, and they start to use this library.
yeah, and what's amazing is that if you look at the number of projects, like well-known, famous, big projects which embed Prom Toolkit, it's quite amazing. Well, I don't know them on top of my head. Maybe you do, but if you have a CLI application that's Python built and that has nice user interface with code with completion, with color highlighting, whatever, pretty much can be sure that it's using Prom Toolkit somewhere or a fork of it. Do you know actually any of those major applications that are using Prom Toolkit?
Yeah, IPython, of course.
Yeah,
I know some of the others as well, like there's Conch. They are, yeah, I don't know all of them.
it's a lot. It's like sometimes I'm just doing like pip install this and I see all the dependencies that come with it and I see Prom Toolkit. Oh, there again. Like, thank you, Jonathan, for your hard work. It's Prom Toolkit actually is it amazes me. If you want to get a good feel on how it works, just download Redkit. Use Redkit client and you will see how great it is. Like with all the completion, all the highlighting, it's always clear. You can do so many things, and it's so user friendly. Actually, that's I think one of the things that makes Redkit successful. It's the user interface, and it's a CLI user interface, and that's just great. So it's an awesome feature. It's great.
Thanks.
And there again, it sounds very simple because dealing with text on the terminal, what can be hard, right? But the way that colors are done on terminal with escape sequence and cursor position and refreshing a part of the screen that's past where you've been in a terminal, it's actually a nightmare in dealing with escape sequence and codes like that, right?
There's a lot under the hood, yeah.
Yeah. Cool.
It's always harder than it seems. Okay, now is maybe a good time to also remind that it was episode 13 that we covered Redkit. So for the people who want to know more about Redkit, we had a Redkit guest on that one. And I'll also take the opportunity to say we are still on X, Twitter, Cisco Tech Stories, and we now have an Instagram account, Cisco Tech Stories, where we post some video bits of our podcast. Well, Jonathan, thanks a lot for your time. It was super interesting to speak about programming and not just networking. So yeah, we have to do some programming, but like you said, we suck at it. So it's good to hear from a real programmer, someone who knows.
A real programmer.
Some people are better than others, right? I'm notoriously bad at coding in Python, so I've done some horrible code. But yeah, as long as it works, at small scale sometimes, but when you have to go bigger scale, it's important to do it properly.
Yeah.
Okay, thanks a lot for your time, Jonathan.
Yeah, thank you.
Thank you.
Bye-bye.
Thanks for listening to this episode of the Cisco Tech Stories podcast. You can subscribe to us on Cisco Podcast Network and SoundCloud or in your favorite podcasting app. You can also find us on X at Cisco Tech Story without S. Thanks again for listening and speak to you next month.
Man with a mission, a magician of code. Streams browser apps, the data flows the mode. Network engineers, he makes them shine. A Zinio wizard, his star designed. Jonathan the coder, magic in his hands. Built applications across vast cyberland. Essential flowing like a river's breeze. Engineer's best friend, bringing them to their knees. PyScript maestro, the web's trusted knight, given the tools to conquer every byte. Streaming all night, browsers in the zone. Jonathan will make your network a throne. Salute to Jonathan, prince of the wire, turning every challenge into gold fire. Asynchronous master, wearing a coder's crown. Pushing the boundaries. Never bounce, never backing down. Network paths broaden under his keen eye. Python's threads weaving patterns sly, from the tiniest bug to the grandest dream. With death fingers, Jonathan schemes. He's the compass in the cyberspace mist, broadening horizons with every twist. Engineers dance on his coded wave, a tech mastermind so brave. Salute to Jonathan, prince of the wire, turning every challenge into gold fire. A Cisco master wearing a coder's crown, pushing the boundaries, never bounds, never backing down.